Let's look at Kepler's laws. So check with your specification to see which of these three you need to know. In my experience, all exam boards expect you to know the third law and be able to use this relationship here, and we'll come on to that one. But other exam boards may or may not expect you to know the first and the second. So the first law is a statement that orbital paths are elliptical, by which we mean this squashed circle. So this is true of orbits. And if we're trying to describe those, then this is the second law. So this is a statement, and we can talk about what it means in a moment. As a planet moves in its orbit, a line from the sun to the planet sweeps out equal areas in equal times. So this is going to move around, this is our planet, around this ellipse, and it's going to move more slowly as it's further away and more quickly as it gets closer. So we end up with this particular arrangement of geometry. So the area of these green segments are equal as it moves along its orbital path, because it's moving more quickly when it's closer to the sun and more slowly when it's far away. And we can actually explain this in terms of conservation of energy, because as the planet is further away, it has a larger gravitational potential energy and therefore a smaller kinetic energy. As the planet moves closer to the sun, it moves more quickly. And we looked at that in the previous lesson about lower orbital heights have a higher velocity. So we've got a greater kinetic energy, and we've also got a lower GPE. So energy is conserved. So this statement is a little bit technical. It's a little bit counterintuitive. And if this is on your specification, then you will need to learn this. The third law, and this is the one we're going to focus in on, is the time period squared is proportional to the mean distance cubed. So we can write this as t squared is proportional to r cubed. What that means is, if we look at all the planets in the solar system, I've just got 4 here, and we consider their time period squared and their distance from the center of the sun cubed, then we get a proportional relationship. That's a straight line through the origin. Most exam boards will expect you to derive this expression and actually derive the formula. So this is what we're going to do now. So first of all, we need to consider that the centripetal force, if we're talking about a planet, is provided by the gravitational force of attraction. So we have mv squared over r, centripetal force, is equal to the gravitational force. So we could simplify at this point, but I'm going to simplify later on. But if we look at this expression here, then we've got mvr and we've got gmmr. So we want to get rid of the v. So we're going to assume that we have a circular path, which contradicts Kepler's first law, but this is the way we do it. So it's moving in a circular path, so constant velocity or constant speed, v equals s over t, where s is the circumference of our circle. So we've got v is equal to 2 pi r over the time period. So instead of writing v on the left-hand side here, we're going to write 2 pi r all squared, which is 4 pi squared r squared, divided by t, which is our t squared, and we have the m and the r from previously. So now we can tidy this up. So we've got little m, we can get rid of that. We've got an r squared and an r, that gives us r on the top. R squared gives us r cubed. And I think that's all tidied up. So we can make t the subject, so bring the t squared from the bottom to the top. So t squared is equal to 4 pi squared over g m, big M, r cubed. So this is our algebraic derivation of Kepler's third law. The t squared is proportional to r cubed. Now, if you prefer, you could write this constant on the other side, in which case it will be the reciprocal. So that will be gm over 4 pi squared on the left-hand side, multiplied by t squared is equal to r cubed. So you can write this as you prefer. So let's have a look at an example. So we've got the mean orbital radius of Jupiter orbiting the sun is this value here, and we assume that is between the center of masses. We're given the mass of the sun and calculate the orbital time period. Okay, so we should have everything. We know big G, we're given that. We know big M is the mass of the sun. We don't need the mass of Jupiter in this case. And we're given the time period. No, we're trying to find the time period. We're given the value of R. So we need to make, first of all, t the subject. So that's going to be the square root of all of this. And then it should just be substitution. But There's a lot going on here in our substitution. So good calculator technique is very, very important. So we have 4 pi squared on the top. That's straightforward. We've got big G here, multiplied by big M, which is the mass of the sun. That's the object in the middle. And we've also got r cubed on the bottom. So watch out for kilometers. So we've got 7, 7, 8, 10 to the 6 kilometers multiplied by 1,000 to give us meters. And then we have our cubed operation there. And you should work out, don't forget to square root. This is a really common mistake in the exam. And you should get 3.73 10 to the 8. Now be careful, because a lot of students miss out on an easy extra mark here because they leave the answer in seconds, and the question is specified it wants the answer in Earth years as opposed to the years of other planets. So we need to divide by the number of seconds in 1 year, which you should be able to do. So that's just 60 times 60 times 24 times 365, and we get this value here. So we would certainly expect it to be larger than an Earth year, and Jupiter's not that far out, so yeah, a little bit larger. That sounds about right.